Okay, thank you all for coming. I think I have roughly between 30 and 40 minutes to give you a presentation. I'll try to keep it very general. I'm coming to you from Hong Kong PolyU. Specifically, I'm coming from ITC, the Institute of Textiles and Clothing. Now, we are a big department. We've got lots of different disciplines, and hopefully I'm going to give you an insight into one of the discipline lanes today. So here is an overview of today's topic. Now, the title of today's topic is specifically fashion and chemistry. I will keep it more general and just try to illustrate the value of science to a textiles-based education. So I'll try to illustrate the critical foundation that science and engineering play to textile study. I'll then give you a general overview of some, I think, interesting applications of textiles or textile hybrid research studies or commercial products. And then I will focus on two specific case studies, dyeing of textiles with a new kind of dyeing method that's been reported, and microencapsulation of textiles with a new kind of product that has been reported. And then at the end, I will finish up for a few minutes on introducing our undergraduate program. So first, hopefully this image is familiar to at least some of you. This is the illustration that your current HK High School exam board uses to illustrate the foundational value of science and the topics that you should cover. Hopefully you'll appreciate that chemistry plays a part in all of these, some more, some less, and that's why it's often referred to as the central science. Science itself is foundational to textiles, and that is hopefully what I will demonstrate in this presentation. I will try to keep the presentation as accessible as possible, so I'll try to avoid any deep mechanisms or theoretical understandings. I'll try to keep it accessible so that you can appreciate the concepts and the applications rather than get too deep into the nitty-gritty of the mechanisms. Okay, so textile technology is basically a hybrid of science, engineering, and then various aspects of design or biology or any other kind of discipline depending on the specific application. So it combines all of these different disparate disciplines together in order to make new materials, make new fibers for new applications. So today specifically, I will explore in the case studies, new kinds of coloration, so new kinds of dyeing techniques, and then new kinds of products and technologies specifically based on coatings. But it's a huge and constantly evolving area. And so before I get to the case studies, I'll just give a general overview of applications. So I'm sure last week, some of you may have attended the excellent talk by Professor Joad Yip on face masks. This is a huge area where fibers, nanofibers, and others, maybe not directly, but indirectly, lots of people are using in order to give better filtration, more effective masks. You have fabric-based technologies used in automotive industries for safer airbags. And then the two I will look at very briefly in this section are gaming applications, so haptic suits, which involves partly some kind of textile based science, as well as architectural applications of textiles. So let's jump into that. So gaming as an industry is huge, many, many billions, and this was only last year. So I'm sure because of the pandemic, the number of people online and playing games has skyrocketed. Now, a lot of people play these games, but there is a limitation in that you cannot get full immersion. So there is a new technology, I think a year or two old now, it's called the Tesla suit. And it's basically a bodysuit, custom made, form-fitting, made of neoprene. And by incorporating electrical engineering and various other aspects and combining it with textile based principles, you can get new kinds of haptic suits. Now, these kind of suits, when you wear them and then you play games or get involved in any kind of virtual reality, they simulate the external environment. So you can feel hot, you can feel cold. If you're playing a shooting game, you can feel impact on your chest. So by having this kind of full immersion, you can get essentially a better experience, both in the gaming world, but it's not just restricted to that. So lots of people in the museum and gallery business are trying to use this kind of technology, maybe not with full suits, but they're trying to use it for interactive VR. And then if any of you have fears of spiders or of heights, then this kind of technology can also be used in exposure therapy rather than being exposed to a real spider or, you know, a real high building. You can instead do this in virtual reality, and so slowly expose yourself and slowly, hopefully, overcome your fears of the respective phobia. So that is in gaming, haptic suits. The second general application is in textiles. So this is architectural textiles. These are adaptive fabric technologies that can be used for building applications. So this is this example, the GIF that you are seeing in front of you, I think is from about 2014 or so about 5 or 6 years old now. So it's a developing area and it's got huge applications and potential. So you can see in this next slide, you can use it to build larger scale structures in and of itself, or you can use it to supplement existing buildings. The benefit of textiles is that they are more flexible, and if you add other properties through various coating or lamination strategies, you can give them extra properties like light, sound, or thermal insulation. So they have huge potential applications in buildings, and they allow you to have new directions in design, in architectural design, and they also potentially, if you get the correct combination of properties, allow you to get, you know, more energy efficient buildings and so forth. So that is the general applications of contemporary textile studies and research, or products actually. But specifically, we're going to look at chemistry and its overlaps with physics and biology, and we'll look at how that is applied to textiles. So specifically, we'll look at dyeing first and how biotechnology is used in dyeing. So global populations are rising. It's slowing in the developed world, but even so, generally, there is an upward trend. This means that the general demand for clothing, for other kind of textiles like towels and bedding, is also continuing to increase. But generally, there is a finite amount of resources in the world, which means that resources are going to become more scarce and more valuable. So the challenge humanity in general faces is how to meet the needs of a growing worldwide population whilst trying to conserve and minimize damage to the environment and to the world. Dyeing itself is a process that gives color to a textile. Usually it's an aesthetic requirement, certainly in developed world when people make buying decisions. It contributes a huge percentage to the decision to buy a certain product. The way dyes work is that they penetrate into a fabric, and so they become fixed to that fabric and give that fabric a specific color. There are thousands of different dyes and even more supplementary chemicals that are used in the dyeing process. The whole point of using all of these dyes and chemicals is that specific dyes have ideal reactions with specific kinds of fabrics. So for example, cotton versus wool. Now, these kinds of different molecular bonding interactions often also require extra chemicals to help with the fixation of these dye chemicals to their substrate. The problem is some of these synthetic chemicals, the auxiliaries, can be materials of concern, and likewise some dyes are also of concern. They're concerning because they may be hazardous to humans who work in factories, and they may also cause some damage to the environment. So it is considered that the textile industry is, according to the Ellen MacArthur Foundation, a heavily polluting industry, and in addition to causing the chemical damage, potentially, it also causes CO2 emissions numbering in the billions of tons. So one of the big demands is to overcome the problems that have been highlighted by big institutes like the World Bank. Dyeing needs to try to reduce water pollution, air pollution, and solid waste pollution, whilst also still meeting the needs of a growing worldwide population. So sustainable fashion and sustainable technology, including chemistry and biochemistry, is becoming the norm and is becoming more and more of interest. So this is where biochemical routes come in. Conventional routes use other chemicals to give color to a textile. One example, for example, is indigo. But biochemical routes can potentially give the same kind of coloration output, the same colored t-shirt or dress, but they minimize the amount of waste produced. So one example is the use of bacteria in the use of dyeing. So bacteria are single-celled organisms. There are lots of different types of bacteria. Each has a slightly different shape, and each can give slightly different colors depending on the specific kind of bacteria you have. This is because each bacteria has a specific kind of pigment that it contains. By taking each of these individual bacteria and their pigments, you can get individual colors. By combining different kinds of bacteria, you can also combine colors to get a third pigment. The benefit of bacteria is that these are biological materials. They are easily biodegradable. So once you've grown bacteria, you can easily kill them either by raising the heat above a certain temperature, or by changing the pH, or any other methods in order to denature the material. The benefit of bacteria is that they can still give good coloration outputs whilst reducing the amount of water, energy, and waste that is used in the dyeing process. So I'm going to try and play this video. Hopefully it works. If it doesn't, not an issue. So this video is just going to illustrate how different bacteria can yield different colors. Okay, so that is an illustration of how different bacteria yield different colors and how you can combine two different kinds or more different kinds of bacteria in order to get a third color. What you can see is that when you try to dye different kinds of fabrics with this kind of bacteria, you can get excellent dyeing outcomes on all different kinds of fabrics. Normally, the problem or the struggle with conventional dyes is only certain dyes can match with certain fabrics. And so you have to have different, completely different dye types for different kinds of fabrics due to the bonding interactions and chemistry involved. In this case, by using bacterial dyeing, those same kind of restrictions are not in play. And so you can get effective dyeing of completely different varying fiber types. In addition, these bacteria can easily be produced on an industrial scale, and they can be used in addition for fabric dyeing. You can use it for cosmetics, for food, for textiles. Again, because it is easily denatured, it is considered relatively safe, unlike some of the other existing dye types. The problem with conventional bacteria that you may encounter in nature or find growing in a petri dish is that on their own, they do not give enough color. They have an uneconomically low yield. So what you need to do in order to get a bacterial output that is industrially viable is to carry out some sort of genetic engineering. Now, thankfully, this stuff is relatively easy to do by specialists, and by doing a relatively simple process of engineering, you can produce bacterial strains that allow for overproduction of pigment, which makes the process economically viable and also allows for long-lasting dyes to be produced. So there are two, I may be wrong, there may be others, but there are two big companies that I know that are working in this area. I think both of them, 3 years ago, they were very small startups, and now they are fairly established and growing fast companies. Faber Futures and Colorifics. Both of them use bacteria. Colorifics uses bacteria from microbes, but it also uses other sources as well. It then extracts those colors, purifies the color, and then puts it onto the bacteria afterwards. Faber Futures can do the colorifics process, but they also tend to grow bacteria and the color that they exude directly onto fabrics, and then use that colored fabric for, as you can see in this example, a silk dress or colored swatches. So the benefits of using bacterial pigments is that they are a natural source, which means that they can be easily biodegraded after their usage. So they do not, or they cause minimum damage to the environment, and the amount of extra chemicals required for their use is much, much less. The other benefits are the amount of water usage is between 10 and 15 times less than a conventional dyeing process, and the amount of energy used is also much, much lower. So instead of doing boiling water dyeing, for example, you can do it at a much lower temperature. So bacterial dyeing is a potentially huge area that may allow for better quality dyed outputs, but also allow for improved environmental impacts as well. So that was the first case study. And that is related to coloration of fabrics or textiles using chemistry and biochemistry methods. The second method is microencapsulation. So in addition to having the basic requirements of color on a textile, you also want to have extra functionality. One of these functionalities is utilizing the skin. So your skin is the largest organ in your body. It's a huge surface area, roughly around 2 meters squared. And it's also semi-permeable. So if you have active compounds, for example, some sort of vitamin or some sort of drug, you can use, allow for that cosmetic or that drug to pass through the skin and directly into the body. Textiles or your clothing is in contact with your skin for, 8 to 20 hours a day, which means that you can utilize textiles as a carrier in order to allow it to interact with the skin, and so allow passage of a certain chemical compound through the skin and into your body. This process is referred to as transdermal delivery. So if we use an example of a fragrance finish, what we find is if you use a fabric softener or some other kind of fragrant compound on your clothing, yes, you can get fragrances onto the textiles, but and it lasts for maybe 1 or 2 washes and you get a good effect. But unfortunately, a lot of these scent compounds, one, they just undergo general diffusion in the atmosphere. There's lots of different kinds of diffusion. This is Graham's, but there's also Fix and various others, which impact and dissipate the strength of the scent. And the other problem is if you have, and it doesn't have to be scent compounds, all compounds can be easily degraded in the atmosphere by sunlight, oxidized, evaporated, so on and so forth. So these kind of environmental stressors can, no matter how good your active compound, cause degradation and environmental dilution of your active compound. So we need a method to try to overcome this. Microencapsulation, it can be used in fragrance finishes, but it can be used in transporting active compounds. This is a method that tries to essentially protect and put a casing around an active compound. There are lots of different compounds that can be used, drugs, fragrances, vitamins, so on and so forth. It's becoming more and more popular. It can be used on textiles, and if any of you use cosmetics, it's very popular in cosmetics. I think I have an illustration in a couple of slides' time. So this allows for active compound lifetimes to be extended. So instead of being degraded in the atmosphere, they are now protected from the atmosphere and can last longer. So this is essentially one very simple architecture of a core shell microencapsulated system. In the core is your active ingredient, whatever it is. It can be any substance you want. And then you have a shell, which is not super strong. So it means that it can either partially or completely break or rupture. So at a certain time or under certain conditions, the shell ruptures and it releases the active compound. In order to get this core shell structure, usually we take this active compound and we place a polymeric shell around it using known chemistries. So in the process, in the microencapsulation process, once we have our protective shell, this now prevents degradation against environmental damage. So instead of now lasting for a short period of time, whether it's 1 or 2 laundry washes or a few days, we can now extend the lifetime of these compounds encapsulated in our shell to weeks or months. So this means that we enhance the stability of our active compound, and we also allow for slow, controlled release. If we talk about different architectures, there are lots of different ones possible. I've given you the simplest one, which is the core shell, but you can have lots and lots of different variations. Again, these are only a limited number of examples I'm giving. So multiple core, where you have lots of small active compounds distributed within a larger permeable shell, or multiple shell if you really want to protect the inner active compound. So basically, the composition is determined by what is your active compound in the center, what material do you have in the outer shell, what is the interface between them. So will it be a permeability mechanism that allows the innards to ooze out, or will it be a cracked shell that releases the active compounds? Now, the release mechanism is also of interest. You can have different release mechanisms. You can do it based on temperature, so that at a certain temperature or above a certain temperature, the shell breaks down and releases the inside material. Or you can do it based on pH. Under a certain pH condition, environment, the shell again breaks down and releases the active compound. So there are lots of different approaches and mechanisms you can use in order to allow the shell to respond to the desired environmental stressor. So here is an example. This is an example of a cosmetic product. I think they use it in a cream, but it illustrates the microencapsulation process perfectly. So you have your active compound, and it's trapped inside what looks here like a very gel-like see-through bead, which I imagine would be easily broken when you rub it on your face. The gel structure, the shell structure would break, and it would release, I think this is a vitamin E active compound. So the benefit of this is when it's not being used, your active compound is protected so that it essentially stays fresher for longer. But then when you want to have your direct impact, you simply crack the shell and it releases your fresh active compound, and you can use it for cosmetic applications or transdermal application. Now, the benefit of having lots of these core shell structures in your, whether it's cosmetic or textile material, is that you can have prolonged release, because not all of these shells break at the same time, so that over time, some will break, some will stay, and then this allows for a consistent prolonged release rather than a huge burst and then nothing left behind. So this kind of approach allows for active compounds to be directly protected. It also allows them to be easily moved around and incorporated within different kinds of substrates. The benefit of using this kind of technology in fabrics is that although it has its active effect, it leaves fabric substrates almost unchanged. So if we have a look at this example, this is a company called Akabada, and they made CBD infused functional activewear. So they have used, if you can see on the top right here, they have used this core shell process in order to encapsulate a CBD active compound, which is it's a compound which is supposedly meant to help with pain and inflammation. Now, the company incorporated this active compound in the shell and put it in strategic parts of sportswear. They were the first company to do it, and they released this product at the end of last year. The benefit of this is supposedly while someone is working out or after they have worked out, you'll get a slow release of this active material, and then that should allow for faster recovery, lower incidence of injury, so on and so forth. So the way this one works, again, it's not a testimonial or a review, it's just I'm using their explanation of the mechanism. There are ECS receptors all over the body, and so the CBD that is contained within their capsules is released in strategic parts of the body where there are a high number of ECS receptors. This is then absorbed through the skin transdermally, and so it has its supposed beneficial effect of, faster recovery, lower incidence of injury, and a soothing effect. So this technology was invented by Devan. I think they're a Belgian company. And what they have found is that this is a completely safe, completely environmentally friendly, skin-friendly process. It is supposedly has its effect, and it maintains this effect over around 40 washes. So if any of you know or have experienced, whenever you buy any kind of clothing, after 40 washes, it will degrade somewhat. It will It will no longer look as good as it did before, but any functionality it may have had will have long disappeared after 40 washes. However, the microencapsulation process, the shell-based protective approach, allows for long-term protection of your active compound. Naturally, there will be a decrease in effect with laundering. If there's less material present, there's less of it that can have a positive effect. But the benefit of it is there is always something present after every wash, and it does have some effect. The other benefit, as I mentioned a couple of slides ago, is that these microcapsules, they have their beneficial impact, but they still allow for the textile, the fabric, to retain its properties. So it still feels soft, it still remains breathable so that, you can sweat, you don't feel gummy and hot when working out or just generally in the Hong Kong environment. Okay, so those were the two big case studies I wanted to use to illustrate the foundational position of science and overlaps with chemistry and its applications in textiles-based technologies and products. So I would finish these final 5 minutes with an overview of ITC, and then if you guys have any questions, you can ask them of me. So ITC is the department I am from. We're at HK Poly U, and we do have a BA scheme in fashion and textiles. So here are the details for you. We do have 4-year undergraduate entry as well as a 2-year senior year entry for those of you who choose to do HD program first. It is a wide and varied load. The first year is common to everyone, but then after that, everyone splits into their different specialisms. We have 5 specific specialisms. Technology is the one that most relates to what I talked about to you today, but we have intimate apparel and activewear, fashion design, which is very popular, knitwear design and technology, and then retail and marketing, which is also super popular. So all of these are excellent programs. We have excellent staff and facilities for each one of these specialisms. So you have a huge range of potential study routes that you can explore. And in addition to those study routes, we also have a huge range of supplemental activities. So almost all of our undergrads go on internships, they go on international exchanges, and then there's lots of exhibitions, factory visits, competitions that our students take part in, and often have won local and international competitions and awards in as well. So there's lots going on, and it's a fantastic environment to be in. Obviously, because of the pandemic, some of these may be attenuated somewhat. In addition to the fantastic program, we also have a huge range of world-class facilities in every one of the 5 disciplines I told you about. So in terms of design and design studios, we have a huge range. In terms of technology, we have fundamental textile engineering workshops, as well as material science and processing workshops as well. So there's and as well exhibition centers and various other things. So it's a huge and very well resourced department. And if any of you are interested in finding out more about it, I'll tell you in a moment. I've gone one slide ahead. And in addition to the excellent learning environment, we also have excellent employment prospects and outcomes for many of our students as well. So there is a huge range of potential careers, many at international brands. So I've had many students go abroad after they've done their degree, whether it's to mainland China or Singapore or the UK or whatever, for trainee programs, for graduate programs, so on and so forth. So if you want to do anything directly related to your undergrad degree, there's lots of routes. If you want to do something indirect but use the principles you learned, again, there's many routes, and there's lots of staff members that can help you plan your career prospects as well. So if any of you are interested in finding out more, naturally we have the website and we have all of the various social media. So please do feel free to chase those up. This is a summary of what I talked to you today. Hopefully some of you found it interesting, and is meant to be an accessible general overview of how science both relates to what you're studying now and also relates to textiles and the potential products and applications that can result from it. So hopefully that was of use to some of you. You can find out more at our website, and if you have any specific questions that you don't want to ask now, I'm happy to take any questions now. Feel free to email the general office as well. So thank you for your attention. If you have any questions, I am delighted to take them now.
Okay, thank you very much again. So I believe you found the presentation very clear and very inspiring. Thank you, Dr. Noor, again. And I hope you all enjoy your wonderful Saturday. So hope to see you next week. So next Saturday, we'll be presenting Olympic and sportswear innovation. The topic will be presented in Cantonese. Feel free to join us. Use the same link to register, just like what you did previously. So thank you again. And finally, I hope you all enjoyed today's talk. Thank you. Goodbye.
Thank you. Bye-bye.
Bye.